are looking into our first lesson on vectors. This tends to be a pretty new concept for people, so this is one of those areas where I hope you watch the videos and come in for help anytime I can help you. Um, so to get things started here, just looking at the idea of a magnitude. When you refer to a speed or a distance, those are both referenced to what we'd call a magnitude. But when you throw in direction along with that magnitude, like 50 kilometers to the east or 10 meters per second to the right, now that you're including direction, we now have what we call a vector. And so that's usually the difference between like speed and velocity. Is speed would include just the magnitude, but when you refer to velocity, you're now into a vector because now we get direction included in that. So keep that in mind moving forward, but speed is a single number like this. Velocity is written as a vector. So when we get down here, there's two ways you're going to see vectors written, two different forms. One is in column form like this, where the first number represents what you would consider to be the x-coordinate. This is the horizontal component. And the bottom number represents the vertical component or the y component that you would see. And so this is one way to write it. So if we were going to look at vector v, so we're calling this guy right here vector v, notice it's starting at point A and ending at point B. So we would call this either vector v, or you could call it AB. Be the same thing. If we wanted to get some real numbers for vector AB or vector v, same thing. You always do the terminal or the ending side minus the initial. So terminal minus initial, so B minus A. So for the horizontal components, we're doing the 4 minus the 1. For the vertical components, 6 minus 2, and that's going to make up vector AB. If we were to change the direction on this and go from B to A, so the arrow would change and would go the other direction. So if I were to go from B to A, now going that direction, I would have to do A minus B if that was the direction I was going to be traveling. So if you look at the way these are written, compare that to what you're seeing here on the next part. This is another way they can be written. Instead of column form, they can be written with an I and a J, where I represents the horizontal component, J represents the vertical component. And so you're seeing those right here for I and J. And so this is just another way that we can write those guys. So like I you can see is the horizontal, represents like the x-axis direction, and then J would be like the vertical component or the y-axis. And so that's just another format that you could write it if you wanted to do it that way. When it comes to magnitude, magnitude basically comes from Pythagorean theorem. If we were to consider this to be A, B, C, and I said, what is the length of AB? And we did Pythagorean theorem, and we did A squared plus B squared equals C squared. Well, to get C by itself, you would have to square root both sides. And so you would say that C equals the square root of A squared plus B squared. And so that's exactly where this formula comes from. It's just Pythagorean theorem to get the magnitude or the length of AB. So keep in mind that magnitude can represent distance. So it's the distance from A to B. You could say it's length. It's the length of AB, or it's the speed. If we're talking about something traveling or moving, it's the speed that it's traveling at. So just a couple examples on that right here, but it's just basically your horizontal component squared plus your vertical component squared, and then if we square root that, you get your magnitude. Notice the looks like absolute value bars. Those are used to represent magnitude. So if it just said find this, and that's all it gave you, we would know that it's referring to the magnitude because of those vertical bars that we see right there. I don't know if you remember any of your Pythagorean triples, but one of the most common ones is a 3, 4, 5 right triangle. So again, that's just all coming from Pythagorean theorem. And you can give those other ones a try. Notice that you're always going to get a positive number for magnitude, always. Because you're squaring both numbers and then square rooting that value, and so you're always going to get a positive. Some of these you'll notice some shortcuts too. Another Pythagorean theorem triple was a 5, 12, 13 right triangle. So if you remember some of those, Those are great shortcuts. So looking at a few ideas more for here for vectors, a couple things laid out. One thing to notice on all of these is all of these would be parallel vectors because they're all running the same direction. They would never intersect each other. Even if one is going this direction and another one is going this direction, we still consider those to be parallel vectors. If they are the exact same direction and the same length, like v and u, we would call those equal vectors. So you'd have to have the same magnitude and the same direction for that to be true. Parallel vectors simply have to be scalar multiples of each other. So you'll notice 2v and v, they're parallel, but they're not equal because they're not the same length, right? One is twice the size of the other. And so this is what we'd call a scalar multiple of vector v, right? If my scalar was 2, then this is a scalar multiple. So they're parallel, but they're not equal. This would also be considered a scalar multiple of vector v. If I were to take vector v and multiply it by -1, right? So I'm giving it a scalar of -1. It creates this vector that you see here. So they're parallel, but they're not equal. And then here's just another scalar multiple concept right there. So moving on down here. So if we were going to take a look at a couple of those with some real numbers, you can see that all those ones that I stated up above were parallel. Take a look at vector AB. So if I was going to go from here to here, right, I do the terminal minus the initial, so 4 minus 1, and 6 minus 2 would give me vector AB. Do the same thing for vector AC. If I did C minus A, I get AC. So notice that if I apply a scalar of 2 to AB, I get AC. So AC is just twice the size of AB, and all that's kind of being stated down here. So you can see this is the idea of a scalar. So if I did AB times 2, then I create AC. And so that's all this one's saying right here. You just distribute the scalar to each component. So you're seeing one more example right there at the top. Same thing. So if this is vector v and I want to apply the scalar of 1/2, I just multiply 1/2 to each of those components, and we get half of v. A unit vector is a vector that has a magnitude of 1. And so here's kind of the general form of what you're seeing on those. But in each case, if I were to do the magnitude a squared plus b squared process on that, I get 1 for each of those. So anytime you are asked to find a unit vector, so if I want the unit vector of AB, then I just reduce each one of these by the magnitude. So we'd say, okay, what's the magnitude of AB, right? If I did a squared plus b squared and I square rooted that, I would get a magnitude of 5. So if I divide each component by the magnitude, we get this, which is the unit vector. Think of unit vector as the way we would talk in terms of like travel. If I said that I was traveling 100 miles per 2 hours, we would say, well, let's reduce that. And instead of saying 100 miles per 2 hours, we would just say I'm traveling 50 miles per hour. And so that would be like the unit form of given like a velocity or a speed like that, is we would say per hour, per single unit. And so that's what you're doing on this. This is like the reduced form of this. So one more dimension can be thrown into these with z right there. So this is something you would have spent a little time on back in honors geometry when you took that course, is that third dimension of z. To get a magnitude on that, not a whole lot different. You just add in the third component. So you're basically doing like a squared plus b squared plus c squared, and then you're doing the square root of that. So you just do all 3 components in there. So here's one example of that. So I got my 6 squared plus -2 squared plus 4 squared, and we get this look right here for the magnitude. If you're going to do a unit vector, so again for the unit vector here for part C, if I divide each component by the magnitude, then I'm going to get this look that you see over here, which is the unit vector. So addition and subtraction of vectors. Take a look at this. This is a really big concept right here moving forward, is this formula that AB plus BC equals AC. So this is a little background on where that comes from. If I just asked you to find vector AC, right, well, one way to do that would be to do C minus A, and I can get the components right here for vector AC. I could do the same thing for BC and do C minus B, and I get BC for right here. So if I did that for all three of those vectors that you see up here, they do fit this formula that you're seeing right here, and this is just to show you that it works. So if this were vector AB, right, I did B minus A to get this one right here, I did C minus B to get this, and I did C minus A to get this. Notice that it does fit, that this does equal the sum of those two. And so this is just a little proof as to why this formula works, but this is a big idea moving forward. And so you're seeing that written out right here. So really big concept right there. So definitely want to take note of this. Really important formula. Think of this in terms of, let's just say that you were right here on the side of a river and you wanted to travel to the other side, to point C. Well, if the river, if the current is moving right here along BC, so that's the current, how would you get to point C, right? You wouldn't jump in straight at point C. The river would push you downstream. And so if I wanted to go from A to C, I would have to travel this direction towards B. So if my boat's traveling this way and the current is traveling this way, then this is the path that I would actually go on, right? So between this vector and this vector, if that's the direction they were going, this is the path I would actually travel on. And so that's kind of the main idea there for vectors. Looking here down here at the last idea, we're going to spend more time on these in part 2 of the notes, but here's just a couple ideas to take a look at for this. So here's one more example along those lines that I'm talking about. If vector u is, let's just say, the direction you set out on your boat. So this is you in a boat going down vector u. This is the way the current is flowing, as vector v is going that way. Well, then this would be the result, or the actual path that you would go down with those two components being added together. So if I did u plus v, it's going to equal vector w, going that direction. So if vector v is going this way, notice if I want to change the directions, I just throw in a negative, and that makes it go the opposite direction. So this direction would be negative v. So in this case, vector w is being represented by the long diagonal, as you can see over there on the left. If I wanted vector w to represent the short diagonal, based on u and v that I already have, in order to get vector w going this direction with the short diagonal, I would have to do u plus negative v in order to get the short diagonal for that parallelogram. Notice one last thing right here. If this is vector u, then this can also be vector u because they have the same length. And if I'm going the same direction, still going to the right, then I can give it the same name. So those have the same direction and the same length, so they are equal. So I can call both of them vector u. Just like if this is negative v right here, then I can also call this negative v right there. So just some real basic additions. One way to make this formula work for you, notice that where this one ends, this one begins. And so if I want to create that look in order to get this, so take a look at fg minus hg, where this one ends, I want this one to begin. So if I just change the sign, I can flip the letters and get this look here. So now where this one ends, this one begins. So if I cut out that middle common component, I get FH. And then same thing on this one down here. This one's just work with some basic numbers. This is just work with some basic numbers. So this is just basic adding to get that one there. And this is just some basic subtraction. If I did v minus u, right, I just throw in the real numbers. So I'm doing the v components minus the u components to create this vector that you see here. But keep this one in mind. This is a really big concept. So this is, again, by changing the sign of this and making those g's both be in the middle, I'm forcing it into this format so I can help make use of that formula.